In this video we will look at the basic mathematical transformations we can apply to the graph of profile. At first let's make the transformation panel visible. Here we can see the transformation panel. It shows the transformation parameters of currently selected flute profile. In this field we can see the length of the flute. It is assumed that the flute length is equal to the length value of last point in the bore measurement table. As you can see, the length of the currently selected flute is equal to 560 millimeters. Let's look at the next profile. The length of this flute is equal to 580 millimeters. The length field of the last point in the measurement table corresponds the flute length. As we can see, these two graphs have the different lengths. That corresponds the length difference that you might have noticed the flute profiles have. To compare the graphs we can apply mathematical scaling. To scale a graph along the length axis, we should apply the normalization transformation. This transformation scales the graph points proportionally along the length axis to achieve specified graph length. To scale a graph manually, we should select the normalization tool. We can scale a graph by dragging the graph border. The length of a graph scaled by normalization transformation appears in this field. As well, you can edit the field to enter a specific value. Now we can see that both graphs have the same length. You can toggle on and off this checkbox to apply or cancel the normalization transformation at any moment of workflow. Let's look how works the scaling transformation along the diameter axis. We should switch on this checkbox to apply this type of scaling. This field corresponds the scaling coefficient used in the transformation. To scale the graph manually, we should select the Scale tool. We can use dragging to change the scaling coefficient. As you might have noticed, the scaling coefficient have changed. Now the both graphs have the same diameter near the top of the flute. The disposition of this profiles shows wide parts of our flute. As a probable decision, these parts of the bore could be filled by any kind of composite material. But maybe we could prefer another strategies of our work. So let's look another example. In this example of profiles disposition, our flute is narrower everywhere along the bore. This disposition can give us a map of grinding the bore to make it wider in essential places. We can apply or cancel the plotting of any flute profile at any moment of workflow. Let's look at the scene in the proportional mode. Let's look at the next transformation named shift. Essence of this operation is the mathematical addition of constant value to the diameter of every point of the measurement table. In other words, the operation shifts the cross-section diameters of the bore on the constant value. Let's activate the Shift tool. We can use dragging to change the constant value used in the addition operation. Now we can say that 1.47 mm is added to every measurement point diameter. This operation shifts up the whole curve on this value. You might notice that shift transformation gives not the same result as the scaling transformation in previous example. The mathematical transformations doesn't change data in the measurement table and can be cancelled at any moment of workflow. So, now we can see the initial disposition of the curves. We can use a different combinations of transformations to find a related dispositions of profiles, and to develop the strategies of our further work.